Hello, friends. Welcome to the Georgia Tech AI podcast. My guest today is Dr. Zsolt Kira, an associate professor and director of the Robotics Intelligence and Perception Lab here at Georgia Tech. In this episode, we dive deep into some of the biggest challenges facing robotics. What does it take for robots to achieve human-level intelligence? How do we build robots that learn, adapt, and work together? Dr. Kira has been at the forefront of AI and robotics for over 2 decades now. It's an absolute privilege that he would take an hour out of his day to speak with me. Beyond his accomplishments as a scientist, he is a genuinely kind individual who doesn't take himself too seriously. And now, I would like to end with a few words from Irfan Issa. The goal of developing true AI is like going to the moon. Machine learning is the rocket fuel that is needed to get us there. Consider a home assistant robot performing tasks like stocking groceries into a fridge. You check the table, you put the dishes into the dishwasher, you fetch objects on command, and you put them back. How do you develop such embodied intelligence systems?
Yeah, so that's actually, of course, a ambitious goal that society has always wanted, something to fetch a drink for you and organize your house and things like that. And I think there's several kind of aspects to it, some of which are currently possible, other which are not. So, of course, a general robot has to start by taking sensor data, understanding like what's in the world around it, and then be able to actually figure out what actions to take next. And so we have made a lot of headway in that. So, of course, sensor processing, like processing images, audio, video, and so on, has made a lot of progress. And then we can now build, reasonable models of what's going on in the house based on such sensor data. We already have models, these days that can actually determine, given all that sensor data, what to do next. And so once you kind of do that, then you have to actually enact it through low level actuation, actually, move the gripper and pick up the object and things like that. So that's the kind of the classical sense, plan, act decomposition that people use. And so we have that pipeline to some degree now. Really, I think the things that maybe are missing these days is that a lot of this kind of has to be done in the context of your home. It has to know, your personal kind of where you tend to put things. If I ask it to fetch me a mug for a particular thing that I want to do, it needs to understand what mugs I tend to use, not to take mugs from the sink, which might be dirty, and so on. So there's a whole kind of layer of common sense understanding, personalization to the human, understanding exactly ambiguous requests that the human might provide and things like that. So I think that's kind of some of the areas that we're working on. Part of that involves also having memory. So actually remembering yesterday I fetched a mug, the user yelled at me. This time, maybe I want to learn from that experience and be able to update how I'm acting now based on all of the history. And, of course, that's a challenging thing because a robot might live in your house for years. And so it needs to remember, understand what to remember, what not to remember. Very similar again to human kind of brain memory.
Yeah, you covered memory. You covered ambiguous requests. Let's get into memory and the topic of continual learning. Can you talk to me about what catastrophic interference is?
Sure. So typically in our current way that we train models is that we train a model based on whatever data it's trained on, and then we deploy it. And when we deploy it, we just freeze the model, and all it knows is based on what it's learned. Of course, what we wanted to do is to continuously learn new tasks. So maybe the robot knows how to, pick and place particular objects, but maybe now I have a new object in my house and I want, it needs to learn how to do that. And so catastrophic interference is where, based on the experience that it's getting now, it tries to learn this new task, but by doing so kind of wipes away some of the learning that happened on the previous tasks, and it can no longer do it very well.
And so there are many problems. You could update the model, you could collect additional training data, but there's an issue with the high cost associated with that. There's also issues with overriding existing knowledge. What's rehearsal?
Right. So rehearsal is actually a very simple idea. Really, it's the concept of, well, maybe we can just keep around all of the experiences that we've had in the past when we learned the original tasks, and just while learning the new task, also continuously keep learning about the old tasks as well. In that way, obviously, you're not as much, prone to catastrophic forgetting because you're still rehearsing all of these old things that you used to learn. Of course, there's, first of all, humans probably don't do this. I don't, when I learn and, how to play a new board game, I don't rehearse all the previous board games that I've played simultaneously. But also, you have to keep around that data that might have privacy considerations. It also has compute implications because now I have to, whenever I learn a new thing, I need to simultaneously learn about the old things at the same time. So that increases the amount of compute that I might need.
Yeah, the privacy concern was definitely, it was well placed when you talked about rehearsal-free continual learning. There's a paper, Coda Prompt, Continual Decomposed Attention-Based Prompting. Can you talk to me at a high level of what this paper was trying to achieve?
Sure. So, and I will give all credit to my students, especially James Smith, who did a lot of this work. And so, really, the idea is he worked a lot on his thesis for actually doing kind of what you were saying, the opposite, replay-free continual learning. So, how do we avoid having to replay all that data in the past? And so, one of the things that have changed as we have continued to work on continual learning, no pun intended, is that we have these huge, amazing foundation models now. And so the things that we wanted to push the community towards is how can we actually leverage these large pre-trained models, and rather than try to solve the catastrophic forgetting in the context of just training these new models from scratch, actually take large pre-trained models and then maybe, tune or learn a small number of parameters within those models. And so what we looked at is kind of learning, doing parameter efficient learning. How do we kind of only tune certain parts of the model? Again, this is very popularized by LoRa and those kinds of methods. And then maybe apply some regularization or some other types of techniques on top of that to make the performance better. And what we found is that you can almost get, upper bound performance that is like, the upper bound in continual learning is often just training on all of the data all at once rather than doing it sequentially. And so we were able to actually get close to that by just having a very nice, well pre-trained model and then adding small amounts of parameters in a regularized kind of course, lots of details of great techniques that James came up with to make that work. And so again, this is kind of a shift in like looking at this problem, moving from training from scratch all the time and preventing catastrophic forgetting to why not just start from these very capable large foundation models.
I see. How does this differ from what we would see typically in reinforcement learning with a replay buffer?
Right. So again, sure, yeah, replay buffers are used in reinforcement learning, of course. One of the key things is, of course, first of all, it's always finite amount of replay, and you kind of, take out the oldest kind of elements and continuously update it. And so again, one of the key things that we want to avoid is like, again, replay of any kind. Even replay buffers, if you're doing home robot, you're not going to necessarily want the robot to continuously store all of the old experiences and what it has encountered in the environment in the past. So one of the key things, again, that we're tackling is scale as well. So you want to not just learn a few new tasks, you want to continuously learn a large amount of new tasks. And so basically that you can't use a replay buffer. It can only scale so much.
Let's talk more about scalability. What are some main challenges when you scale episodic memory to real robots, and where could Coda Prompt fit in?
Right. So again, in Coda Prompt, we use a replay free method. So it scales much better. There's, of course, several characteristics of scale. One is just the computer science, how much memory, how much compute does it take? But on the other hand, there's also performance, right? And so in that paper, I don't exactly remember how many tasks that we sequentially learned, maybe like up to 25, up to 50, something like that. But of course, even our performance continues to degrade as you add more and more tasks. And this is actually some of the unsolved problems in continual learning, is that pretty much all methods currently look at some relatively small amount of new tasks that you're continuously learning. Of course, if you want a robot to live in your house for years, it will have to learn probably thousands, if not tens of thousands of new things. And so that's really an unsolved problem, and kind of relates to some of the things you're talking about, like episodic or other memory. I think one of the key things is replay buffers, for example. There's lots of work, of course, on like exactly which experiences should I put into that replay buffer? Can I maybe pick, figure out which ones are irrelevant or not very helpful to my learning, which ones were more important? But still, we don't have very good methods to take huge streams of data across, months or years, and then figure out exactly how to retain and what to retain in the brain, or in memory. And again, the brain does this somehow with unknown techniques. A lot of it is actually tied to things like emotions, right? Um, Things that are like salient to you emotionally tend to be recalled better, things like that. We have no such notions in robotics. I think that's again an open area of exactly how to do this long term.
Let's talk about this more. What are some gaps that you see between biological and artificial memory systems?
Right. So again, there's lots of gaps. So first of all, a lot of our memory systems are pretty much just flat. Like there's a memory system, and we maybe store some vectors or knowledge in there in the brain. And I'm not a neuroscientist, but there's like dual memory kind of frameworks. Right? So there's short term and long term memory. The people have shown, of course, through sometimes things like, you know, people encountering like damage to their brain or diseases where they might have one but not the other, right? Showing that they are two distinct kind of things. Again, there's ties to saliency in some way, either to the task or to your emotional kind of state at the time. Um, and so, the retrieval is of course very efficient. And I would say one interesting thing about human memory is that often it's very associative, in the sense that, like, you might remember, or you might smell something, and that ties to, you remember this new thing that, or this old thing that like tied to that smell. And then maybe that new thing spurs recalling of additional things that you encountered. And so it's kind of like this rolling associative kind of process. And again, yeah, there's not really a computational kind of analog that we use that for that right now.
There's also the parallel with neurogenesis that I recently read about in one of your papers, that it tends to be higher. You tend to generate more neurons when you're exposed to a diverse set of experiences. Are these particular insights something you try to replicate in your own work?
Yeah, so I mean, currently not necessarily, but there are definitely people who are looking at that. So I think, again, the brain is super complicated compared to our current models. You tend to learn a lot as a kid, and then there's a pruning stage at some point where, the connectivity is whittled away. And so you kind of, are growing new connections, new cells, and then at some point there's also some pruning mechanism. And so there are for sure methods that start to try to tackle that, where you have, if you're learning multiple tasks, maybe I want to learn new pieces of neural network for that particular task. But I would say that's, yeah, kind of a little bit a more difficult way to approach it. It's hard to understand, when to grow new connections and, sub networks, how to prune it away. There are people working on all these problems, but they're very hard to do. And again, if you want to test this long term, it's just a hard thing to scientifically study, because you want to, understand how these mechanisms happen, not over the span of a few new tasks, but, a lifetime of a robot.
Absolutely. And going back to the start of the conversation, you mentioned memory, but you also mentioned ambiguous requests. A task that you might provide as a language instruction might be interpreted very differently by a robot. And so one of your papers, Generalized Embodied Agent, one of the very recent ones, It focused on a multimodal LLM agent. You can complete tasks from natural language instructions. One thing that stood out to me is, when you translate language instructions into actions, how do you ensure that your model can maintain that alignment between the user's intent and the robot's execution?
Right. So in that work, really our approach there is scale. Just throw, millions of experiences and try to learn from that. Very similar to how language models became good. Of course, the scale that we're working at is nowhere near that. And so you do get some generalization and some robustness to ambiguity just from that, because you've seen lots of things. You kind of tend to learn inside the model what people tend to ask for and why. And again, if not, then you don't do the task well, and then you update your model to improve. So you get some, robustness to ambiguity there. But again, none of these are, foolproof solutions. Actually, we have some work coming out with Meta that looks at actually how to, have a robot determine when to ask a question of a human and interpret the answer to improve the performance. So if you're asking again, like, bring me a mug, and the robot doesn't really know exactly which mug you're talking about. What are you going to put in it? Is it, Coke or orange juice or something else? Then it can actually decide to ask a question of the human, and then the human can answer and disambiguate the requests. And, this happens naturally all the time with humans as well. It's not like everything you say I can perfectly interpret. Disambiguate sometimes. I'm not sure exactly what you're talking about, so I can ask you questions, right? Or maybe even rephrase it to you, and you can kind of confirm or deny whether, I'm accurately portraying it. So there's lots of, I think there's both sides of the coin, which is trying to improve the robustness just through scale and giving it access to a lot of experience, but then also incorporating things like communication with humans.
Yeah, scale definitely seems like a promising idea, but how do you personalize? Uh, I have a different way of saying something. You might have a different way of saying something. How do we incorporate that?
Right. Exactly. And that's, again, that ties to the previous discussion of continual learning, right? Ultimately, it's not, I don't believe it's going to be the case where we'll have one huge model for all of society, and then it'll be put on all robots and it'll be frozen and not learn again. Really, it'll have to come into a new home again, just like any other new person that comes into your home. They have to acclimate, understand, start to learn, your particular ways of being. And again, I think there's the questions of how do you update the model to do that. These days, by the way, there's lots of what's called in context learning or prompt learning, right? Where you can actually not update the model itself, but actually just manipulate the inputs that you're providing it. So retrieve things in memory and then, actually just put it into the model. So, this happens with OpenAI and others these days. ChatGPT remembers all your previous conversations and can actually retrieve relevant snippets. And then it remembers, oh, yes, you're a student, and, this is your life, and some aspects. And that informs the answer to the new question that you're asking. So similarly, we can also do that. We can always store text or image or other types of data um, in memory, and then try to retrieve that and manipulate the inputs to the model. Um, so I think these are all ways to, again, just condition the model's outputs on your personal life and things that it has encountered with you.
What I find fascinating about this paper, though, is the topic of a multi-embodiment action tokenizer. You're handling diverse tasks as opposed to training on a single one. Can you expand more on this and how it differs from uniform discretization?
Right. And again, I'm going to give credit to my student, Andrew Zsolt, who's did a lot of the work, and this is with Apple. Yeah, so there, I mean, really, there was a previous paper where we looked specifically more at this as well. And really, the idea is that the way you tokenize outputs is, can be different from language, right? And there's two kind of cases, actually. There's a case of what's called discrete action spaces. So, for example, if you have a model that isn't sending like low level controls commands to a robot, but instead is actually just selecting from skills, for example, like pick, place, navigate, open the fridge, and so on. That's like a discrete kind of set of actions that you can do. And so in that case, actually what we found is that the output action tokenization that worked the best was the semantic meaningful token. That is, you can take the model already has tokens for these particular concepts like picking or placing just from language, right? And so actually, if you output those tokens as the output action and then decode it, it performs better. There, I really enjoyed this result just because it kind of shows that you're leveraging the existing common sense knowledge that the model has inside. And if you output things that make sense with respect to things it knows already, and with respect to the physical thing that you're trying to do, then it actually works better. If you're outputting like low level commands, like angles, torques, and things like that, then what we found is that if you have like an explicit learning phase in the beginning that learns a discrete tokenization of this continuous space, that works the best. So this is called the VQVAE, and there are something called residual VQVAE. But basically it just learns like what's called the code book, which is a set of tokens, and so that turns a continuous space into like a discrete set of potential outputs. And again, we found that worked the best for these tasks. And like you said, I think the coolest part is that, these methods allow us to train one model that can do all of these tasks, both navigate a robot in simulation, to pick up objects, but also play Atari games and navigate the Apple's phone GUI to perform tasks and things like that. So I think that was a really cool result.
Yeah. I want to ask you about some surprising things that you saw from your paper. The first one, like you said, you trained it on diverse domains. But I want to ask you, were there some unexpected synergies where some skills from one domain translated into another?
I would say, I think it's always hard to understand like which tasks will or will not aid each other. I think before we did the work, had some intuition that, of course, like different robotics tasks might help each other. Whereas, like, if you have one robotics task and like Atari game or something, maybe the synergy will not be that much. So I would say, I think it's expected. I think one of maybe the more surprising to me was that there wasn't a lot of interference. Typically, this notion of multitask learning, like learning many different, very heterogeneous tasks with one model, is actually a really hard problem. And what you often find is you have a lot of interference. That is, learning, new Atari tasks somehow interferes with these other tasks. And so when you just throw naively together everything, the combination doesn't always just improve. And I think we didn't really find as much interference as at least I had thought based on my knowledge of the difficulty of multitask learning.
And you're saying this is primarily because of the base model, Lava 1 Vision. That was the reason?
I think so. I think basically that we are finding these days that for anything, and a lot of this was, again, reinforcement learning. So learning from experiencing the actual task or world. And there's these days, I think, an understanding that's beginning to happen that if the base models are really good and they already have soaked up so much knowledge from the web and know so much, that really, it helps on a lot of things, both even just learning from reinforcement learning. Sometimes reinforcement learning from scratch or from doing it from poor base models doesn't help as much, but also, yeah, preventing things like interference.
And one other surprising fact about this paper was the role of reinforcement learning. One line stood out to me. Success rates dramatically boosted from 57% to 83% in habitat pick just because RL fine tuning was applied on top of supervised learning. Why did that happen?
Yeah, so I think, again, we have to think about the alternative to reinforcement learning, which is how a lot of the base models are trained, which is what's called learning from demonstration or imitation learning or supervised fine tuning, all the same, different words for the same thing. And really, the idea is that you have humans or planning systems or other things that provide actually how to provide or how to do the task step by step. So you're providing a demonstration. Like if you want to pick up a cup, well, actually move your arm in these ways and grip, and this is picking up a cup. There's a lot of advantages to that. It doesn't have to explore. You have an expert really honing in on exactly the set of actions that have to be done to perform this task successfully. On the other hand, it's not quite enough because, for example, the robot is not exposed to failures or things that are being done wrong. And so once you learn from demonstrations and then you try to deploy it, then the robot might mess up a little bit. Then it finally finds itself in a situation where it hasn't really encountered. And so it doesn't even know what to do. because after the failure. And so that's why this combination of first we get a decent model with imitation learning, and then we fine tune with reinforcement learning, where it's actually taking that base model, trying different things, exploring the world, failing, and then learning how to recover from those failures. And that's really an important aspect of learning, not just learning the correct way to do things, but also learning how to react when, inevitably something bad happens.
Yeah. How would this translate to a real world setting, which would happen very often where things go wrong and you have to recover?
Yeah, absolutely. I mean, and as we know, the world is very chaotic, and I can, as the robot is doing, sometimes maybe adversarially. So I know there's a robot actually delivering food in my bowling alley, and so sometimes my kids likes to mess with it, or we like to get in front of it. So people will try to adversarially maybe mess with it, but also again, like lots of random things happen. And this is actually something that's really important in robotics, which is what's called like the long tail kind of problem. That is, yes, you can train it to act under many situations, just like self-driving cars, but once you start to deploy it and it gets millions of miles under its belt, all sorts of crazy things will happen, right? I think there's an example of a bicyclist with a stop sign on his shirt on the back of his shirt. So the car is like, what is this? And so again, I think the more you experience the world, the more you will experience these very rare things that happen, but you have to really react to and be robust to. Otherwise, either you'll fail or even worse, can harm humans or yourself. And so we really need this level of robustness.
I really am curious. You've been in the field for, I'd say, 2 decades now. Yeah,
Making me sound old, but yes.
it wasn't my intention. But you started with an interest in robotics, and this is before robotics was even cool. What attracted you to the field?
Yeah, so I mean, I would say actually my interest started from just general AI. I think, like a lot of other students, was inspired by a faculty that taught me, my first AI class in undergrad, and that really inspired me, along with some other CS classes that actually talked about intelligence, the brain, like figuring out how to replicate the amazing things that humans can do. And so that's really, where my interest started, just understanding intelligence. And then, I ended up in a lab that did robotics. And I think, of course, robotics is the ultimate test of whether your algorithms work, because it has to work in the physical world. Again, be robust to all of these random things that can happen. And so I think that's one of the key aspects, is that intelligence, just for its own sake, and in a computer, I mean, it is amazing, of course, ChatGPT and all these things. We don't necessarily need embodiment, but I think embodiment really forces the question, right, of can you actually, do all these tasks in the real world in a consistent, reliable manner? And that's, again, one of the hallmarks of human intelligence. We're very robust to all sorts of things, and we learn adaptively, all these kind over time and things like that. So I think it's a great like test bed for that.
Was this always the vision for you, or has that developed over time?
Yeah, I mean, I think my interest has always tended to be generalization. That is, I don't care so much of how it performs on the things that it was already trained to do, because ultimately, I think I was a believer that, machine learning can do that given enough data of that type. It's really, can you generalize, right, to new situations? And language has been amazing. It's great that we have language models now, because that is kind of a fuel for generalization. You may learn with a few kind of concepts, and then you can generalize to semantically similar concepts because you have similar linguistic representations. Yeah. So I've always been interested in just, the generalization ability of humans. We can do anything. I can play chess. I can drive a car. I can play soccer. And when you have kids, I think you see how quite amazing they are, but also how fast this intelligence develops. And actually in a much more data efficient manner, at least in terms of the tasks and things that they're exposed to, compared to the models that we have now. So I think that's what, excites me, of being able to replicate those amazing capabilities.
So when we talk about few-shot learning, we've already spoken about the role of foundation models and pre-training. But I would love to understand from you, what are the key things we would need to keep in mind over the next decade or so when we talk about robot generalization?
Yeah, so I mean, I think few shot learning is, of course, I mean, one of the aspects again tied to continual learning and all those things, in the sense that if you have a robot in the house, I'm not gonna want to like show it 10 million times how to do something. I want to show a few new examples of a new task, and it needs to again learn without forgetting the old things that it knows, right? I think one thing that I am thinking about, of course, I think we've already talked a little bit about human interaction. I think the ability to learn from natural human interaction or robot interaction even is important. So again, I want to be able to honestly just talk to the robot, tell it, maybe show it one or two times how to do something, and then I'm going to expect it to know and learn from that, right? And that's really a very difficult problem. It's learning not just from demonstrations, but even just from linguistic descriptions, right? Like, no, in order to fetch the mail, it's the same thing as fetching my cup, but go to the mail room. The mail room is here, and so on. And so linguistically describing either spatial, temporal, or semantic concepts to the robot, and then how does the robot even update its knowledge based on that? I think that's something that actually I haven't even seen a lot of work on currently, and I think is really exciting and to think about. So learning not from few shots, not just you know in a way where I'm actually showing it demonstrations, but also giving it again ambiguous high level descriptions. Can it learn from that? Yeah.
Yeah, you talked about language instructions. I keep thinking about the different modalities that you could consider beyond just a simple language instruction. It could be the tenor, the tone of my voice, the facial expression. And humans are amazing at this, just going around and capturing all kinds of modalities. How can robots be able to integrate so many different kinds of modalities and come to a unified understanding of what's being said?
Right. Yeah. So that's exactly right. And I mean, one of the cool things that actually I've always liked about robots is that they do have lots of sensors. Often you have, of course, cameras, but also depth sensors that tell you how far things are away from you, audio. Sometimes they have some specialized, radar or other types of sensors. And so I think these days we are starting to get to models that can integrate all this information. But I would say they're much, earlier than, for example, just pure language models. And I think we already have some idea of how to start about it, right? A lot of the architectures, like transformer architectures, are amenable to just throwing in modalities of different types. But I think there's lots of, again, challenges. For example, during training, you're not going to really have access to all of the sensor modalities you're expecting it to process at the same time across a huge swath of training data. You might have some training data that might have, for example, YouTube videos that has audio and video. You might have some onboard robot data that has like video and maybe depth sensors. And you have mixtures of combinations of these multimodal data sets. And so how do you combine that into learn a unified multimodal model? I think is very challenging. And so, and there's the other aspect that you talked about, which is like very subtle cues, right? That you need to pick out from this data, not just, you know, what is the 3D around me, like the 3D world, where are objects, but also subtle audio cues, facial expressions, those kinds of things. And those require even more specialized models. Right now, it's not like we have one huge model that can do all of these. It can actually take out the expressions in your face given a video. Really, if we want to do best at that right now, we need to train a special model to do that. If we want to do like audio intonation and other things, we need a specialized model for that. I think we're quite far from a unified multimodal model that can do all of these very specialized tasks, as well as the individual models themselves.
Right. A lot of roboticists and researchers focusing on AI, they do talk about how their work actually helps them understand human beings better. Humans have been really successful as a species because we've learned to cooperate really well with each other. How do you see this translating to robots, where there's a collective intelligence that can emerge?
Yeah, absolutely. Yeah. And I think, I mean, I already mentioned, right, human robot communication, but also robot to robot communication, which can happen across robots. But I think what you're alluding to is, unlike humans, you can actually link the robot's brains across the internet, right? And so, yeah, actually, we did think about this. We haven't worked a lot, but we had some kind of early ideas that we were talking about. For example, if you have many home robots, right? You want to do two things. One is we talked, you want to actually combine all the knowledge and experiences that all the robots across all the homes are learning and kind of generalize out of that and learn a new kind of global model that you can then distribute to other new robots. And this relates to something called federated learning, where you have each device learning by itself, and then you want to combine all of those to one model on the server. But then you also want the other thing, which we talked about, which is personalization, right? Where you want, okay, now we have an amazing new global model, but I also wanted to not forget for each home, what are the unique properties of that home? And so I think, yeah, this kind of tension or trade off between like combining all the knowledge across the robots such that you can, as we mentioned, scale gives you generalization, but also retaining the personalization as well. These are all kind of very difficult problems. And again, federated learning, and actually we have some papers on federated continual learning I think are really relevant, but there's a lot of work for sure to continue to do this in this area.
One thing that amazes me about your work is just how broad ranging it is. We could talk about collective intelligence. I could refer to your who to com paper, when to com paper. There's a paper for just about every area that we've covered. I'm wondering, looking back on your career, what is something that you're proud of when you look at your PhD self? What are some things that he did that you're really proud of today?
That's an interesting question. So I'll answer it two ways. One that doesn't answer your question, but one that does. So, I mean, definitely, I think something that I'm proud of is, I tend not to just follow the existing trends, but actually think about the future in terms of what are the limitations. Okay, like there's the hot stuff that we're all working on now, but let's say it's all successful. Like what next? What are the limitations that will remain, right? Even as a PhD student, I always advocated for feature learning back when feature engineering was a hot thing, or like the common way to do it. Of course, I wasn't smart enough to know exactly how to do it, but I was always about combining learning and robotics even early on before it was popular. So, I think kind of just maybe more holistically thinking about the broad topics rather than being bogged down into, like, okay, this is my favorite tool or favorite mathematical method or whatever that I'm excited about. You know, so I feel like I did that, yeah, relatively well. I think in terms of the most thing I'm proud of, I think would be my students, current PhD students and graduated PhD students, just because I think one of the things that you were mentioning, which is that my lab does do a whole lot of different things. Part of that is because I try to encourage students to follow their passions, and have students understand. Of course, it's a hard thing to even figure out, like, what are you passionate about, and then follow that, right? And so that's why we tend to have a lot of disparate works, but they all kind of collectively move towards improving overall intelligence, robustness, generalization in robotics, and multimodal models. And so I think, definitely very proud of all my students who've done amazing jobs at forming these new kind of sub areas, like you were alluding to, that sometimes even get picked up by other groups and as like new sub areas. So yeah, definitely, yeah, very proud of my students and all the things they're accomplishing after they leave as well.
Looking into this century, say that your kids came up to you and said, "Hey, Dad, I really want to work in robotics and machine learning." What piece of advice would you give them to navigate this world?
Sure. And I will say, the more I talk about AI and robotics to my kids, the less they want to do it. So I try not to push it. Although my son is actually this summer trying to build a robot. So we will see. So yeah, I think, my advice again is always just follow your passion and enjoy the process and just the journey. Maybe is a bit cliche, but I think a lot of times we focus on kind of goals or deliverables or like, doing well, or, oh, what if this particular area is not hot right now and maybe it'll just die off? Should I like switch to something else just because of that? Or I need to get a job and things like that. I think ultimately in life, you want to, minimize the things that you don't want to do and maximize the things you're passionate about. And so really finding your passion is the first hard thing, and it could evolve. Even me, my things that I'm interested in evolve over time as, of course, the field evolves. And just taking all opportunities that allow you to potentially do the things that you're passionate about, right? I think sometimes one of the things that maybe more junior people tend to do is self-filter, like, oh, I'll never get that fellowship, like, oh, this, opportunity is like not relevant to me or whatever. And instead, I think you should not self-filter, aim for taking all opportunities that come in your way to that will increase the chances that you can follow your passion, and maximize the things that you want to do.
Awesome. Well, Professor, it was an absolute pleasure speaking with you. I'm just very delighted by the fact that you could cover so much.
Absolutely, yeah, thanks. No, I really appreciate the invitation. I think it's a great opportunity to. It was really interesting discussion and topics.